You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Advanced methods for securing data have emerged as organizations face increasingly complex threats and compliance challenges. Beyond familiar techniques like encryption, masking, and access control, these advanced approaches focus on protecting data while it is being processed, enabling secure collaboration, and strengthening trust in integrity. Examples include homomorphic encryption, which allows computations on encrypted data without exposing it; secure enclaves, also known as trusted execution environments (TEEs), which isolate sensitive workloads; and token vault architectures that consolidate tokenized data under tightly controlled safeguards. While still maturing, these methods expand the toolkit of defenders, where traditional controls may not be enough. Trusted execution environments, TEEs, often referred to as secure enclaves, protect data while it is in use by isolating workloads from the broader system. TEEs create protected regions of memory within processors, ensuring that even privileged users like system administrators cannot view what is being processed. For example, a TEE may run a secure payment application, keeping encryption keys and transactions hidden from the underlying operating system. This isolation reduces the attack surface, protecting against both external attackers and malicious insiders. TEEs illustrate how hardware can enforce confidentiality even during active computation. Homomorphic encryption represents a groundbreaking but resource-intensive approach to data security. Unlike traditional encryption, which requires decryption before data can be processed, homomorphic encryption allows computations to occur on encrypted values. The results, once decrypted, match what would have been obtained had the operations been performed on plaintext. Conceptually, this means sensitive datasets never need to be exposed in their raw form. For example, a cloud service could analyze encrypted healthcare records without ever seeing patient details. The trade-off, however, lies in performance. Computations are far slower and require significant resources, limiting practical deployment to specialized use cases today. Data provenance and integrity controls ensure datasets remain trustworthy by tracking origin and verifying authenticity. Provenance establishes a chain of custody for data, documenting where it came from, how it was modified, and by whom. Integrity mechanisms such as cryptographic hashing and digital signatures verify that data has not been altered in transit or storage. For example, a blockchain ledger may preserve the provenance of supply chain records, while hashes confirm they remain unaltered. These controls are critical for preventing tampering, ensuring that decision-making is based on accurate and reliable data. Secure multi-party computation, SMPC, is another advanced method that allows multiple participants to perform computations collaboratively without revealing their individual inputs. Instead of pooling raw data, each party contributes encrypted or partial values, and the computation produces a result without exposing underlying details. For instance, competing banks might use SMPC to jointly detect fraud trends without sharing customer-specific data. By enabling collaboration while preserving confidentiality, SMPC addresses the tension between data sharing and privacy protection in highly regulated industries. Hardware-assisted protections add another dimension of security by anchoring trust in specialized components. Trusted Platform Modules (TPMs) provide secure key storage and system integrity checks. Hardware Security Modules (HSMs) offer tamper-resistant environments for cryptographic key management and digital signing. Secure elements, often embedded in mobile devices or smart cards, protect identity credentials and payment data. For example, an HSM may generate and store keys used for encrypting credit card transactions, ensuring they never leave protected hardware. These hardware-backed controls reduce reliance on software alone, offering stronger resilience against tampering and theft. Privacy-enhancing technologies, PETs, form a broad category of advanced tools aimed at reducing risk while enabling legitimate data use. These include anonymization, differential privacy, homomorphic encryption, and SMPC. PETs allow organizations to extract value from data, such as performing analytics or research, without exposing sensitive details. For instance, differential privacy adds statistical noise to datasets, enabling population-level insights while protecting individual records. PETs are increasingly being recognized not only as technical measures but also as strategic tools for regulatory compliance and ethical data stewardship. Policy-driven access controls extend beyond static permissions by enforcing dynamic, context-sensitive rules. Rather than granting access based solely on identity or role, policy engines evaluate factors such as location, device posture, or time of day. For example, a finance employee may access sensitive reports from the office but require multi-factor authentication when working remotely. Policy-driven systems adapt protections to the situation, ensuring security remains proportionate to risk. This approach reflects the broader movement towards zero-trust architectures, where no access decision is assumed to be safe without verification. Auditability and immutable logging provide the evidence organizations need to prove correct handling of data. Immutable logs, whether stored in blockchain-based ledgers or write-once-read many (WRM) storage, ensure records cannot be altered retroactively. These logs document access, changes, and administrative actions, creating transparency and accountability. For example, an immutable audit trail may show precisely which administrator accessed a secure vault and when. By guaranteeing the integrity of these records, organizations can respond confidently to regulatory inquiries, forensic investigations, or customer concerns about data use. Risk-based selection of advanced methods ensures resources are applied where they add the most value. Advanced protections often come with significant performance, cost, or complexity trade-offs. Deploying homomorphic encryption for routine office documents, for example, would be wasteful, but using it for highly sensitive healthcare research may justify the cost. A risk-based approach evaluates the likelihood and impact of threats, applying advanced techniques only where traditional controls cannot provide sufficient assurance. This perspective balances innovation with practicality. Performance and cost trade-offs must always be considered when adopting advanced cryptographic protections. Homomorphic encryption, SMPC, and TEEs may demand higher processing power, specialized hardware, or additional licensing costs. These overheads may limit scalability or increase operational expenses. For example, organizations may find TEEs feasible for securing specific workloads, but impractical for broad deployment. Evaluating trade-offs ensures advanced protections strengthen security without crippling usability or budgets. Decision-makers must carefully align protections with both security needs and organizational resources. Ultimately, advanced data protection techniques should be viewed as complementary tools rather than replacements for foundational practices. Encryption, access controls, and monitoring remain the bedrock of data security. Advanced methods, homomorphic encryption, TEEs, SMPC, and PETs, add new dimensions where traditional controls fall short. For example, PETs enable analytics on sensitive datasets while respecting privacy. By layering advanced techniques with existing protections, organizations build adaptive, resilient strategies. These emerging tools represent the next frontier of defense, allowing security programs to evolve alongside technology and regulatory landscapes. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Integrating trusted execution environments (TEEs) into application architectures requires careful planning. Applications must be designed to route sensitive computations into the enclave while less sensitive processing remains outside. Key management is central here. Cryptographic keys must be provisioned into the enclave securely, often using attestation processes to confirm the enclave is genuine. For example, A secure enclave running a payment module may be provisioned with encryption keys only after the hardware demonstrates authenticity. This integration pattern ensures that data and keys are processed in protected zones, minimizing the chance of compromise. Choosing between homomorphic encryption, secure multi-party computation, pseudonymization, or tokenization requires evaluating business goals and risks. Homomorphic encryption and SMPC are suited for scenarios demanding high privacy, where sensitive data must be processed without exposure, such as collaborative medical research. However, they can be costly and slow. Pseudonymization and tokenization, by contrast, are simpler and often sufficient when real values are unnecessary outside their originating systems. For instance, replacing credit card numbers with tokens reduces exposure without the heavy computational burden. The decision rests on balancing privacy guarantees with practical performance needs. Governance requirements grow more complex when deploying advanced privacy-enhancing technologies. PETs. Testing and validation must confirm that methods like homomorphic encryption or enclaves function as intended without undermining performance or business processes. Governance may also require independent security assessments to verify that protections are robust. For example, before adopting differential privacy techniques in analytics, organizations should validate that added noise preserves privacy while still producing meaningful results. Strong governance ensures PETs are deployed responsibly, transparently, and with clear accountability for outcomes. Auditing and attestation workflows are key for hardware-backed protections. Enclaves and secure elements often provide attestation mechanisms that prove they are genuine and operating in secure modes. Audit workflows collect this evidence, linking it to data handling logs. For example, a cloud service may use remote attestation to prove to customers that workloads are processed in verified TEEs. Immutable logs then record this assurance alongside data access events. These workflows combine technical guarantees with documented accountability, reinforcing trust in specialized hardware protections. Operational concerns like availability, scalability, and recovery must be addressed when relying on specialized protections. TEEs or HSMs may become bottlenecks if workloads grow faster than hardware capacity. Failures in specialized hardware can also complicate recovery if backups or redundancy are not planned. For example, if an HSM cluster fails without replicated capacity, decryption keys may become inaccessible. Organizations must design architectures that anticipate outages, ensure redundancy, and allow secure recovery without exposing sensitive material. Operational resilience is as important as cryptographic strength in real-world deployments. Hybrid approaches often provide a balance between practicality and advanced protection. For example, conventional encryption may secure datasets at rest, while TEEs protect only the most sensitive processing steps. Similarly, pseudonymization may reduce the footprint of sensitive data, while SMPC handles only critical collaborative computations. By blending methods, organizations reduce costs and complexity, while still gaining strong protection where it matters most. Hybrid designs acknowledge that not every workload demands advanced cryptography, but that some processes benefit significantly from it. Selecting vendors or open-source solutions for advanced protections requires careful evaluation. Vendor offerings may provide integrated platforms with support and certifications, but come at higher costs. Open-source tools may offer flexibility and transparency but require greater internal expertise to deploy securely. For example, organizations adopting SMPC might weigh the ease of a commercial solution against the adaptability of an open-source framework. Vendor lock-in, interoperability, and community trust all play into the decision. Thorough evaluation ensures the chosen toolset aligns with long-term security, compliance, and operational needs. Roadmap planning is critical when introducing advanced protections. Organizations often start with prototypes to validate feasibility, then move into controlled pilots before scaling broadly. For example, homomorphic encryption may first be tested with small datasets to measure performance impacts, then piloted in a limited analytics function. Only after proving value and manageability should it be extended across the enterprise. This staged approach reduces risk, ensures stakeholder buy-in, and allows teams to adapt incrementally. Roadmaps align advanced protections with organizational maturity and evolving business priorities. Training and operational readiness are necessary to support novel protections. Advanced techniques require new skills from administrators, developers, and security staff. For example, deploying enclaves demands understanding attestation workflows, while using homomorphic encryption requires cryptographic literacy. Without training, errors in configuration or misuse may undermine security gains. Training programs and clear operational procedures equip teams to manage, troubleshoot, and adapt protections effectively. Building this readiness ensures advanced methods deliver lasting value rather than creating fragile, misunderstood systems. Measurement and assessment confirm the effectiveness of advanced protections while identifying residual risks. Metrics may include performance benchmarks, error rates in classification, or the reduction in exposure of sensitive data. For example, measuring how differential privacy affects analytic accuracy helps balance protection with utility. Risk assessments should also evaluate what vulnerabilities remain, since no technology eliminates all threats. By quantifying both benefits and limitations, organizations can make informed decisions about continuing, expanding, or revising their use of advanced methods. Legal and regulatory reviews are essential before deploying novel cryptographic techniques in production. Some methods, like homomorphic encryption or SMPC, may not yet be explicitly recognized in compliance frameworks, raising questions about audit acceptance. Organizations must engage with regulators, auditors, and legal counsel to ensure that advanced protections satisfy obligations. For example, data anonymized using PETs must still align with GDPR definitions of anonymization. Legal review ensures innovation strengthens compliance rather than creating new liabilities or misunderstandings with oversight bodies. Ultimately, advanced data protection methods must be chosen judiciously and integrated into a broader security program. They are not silver bullets, but complementary tools that extend defenses where traditional measures fall short. By combining TEEs, PETs, and cryptographic innovations with established practices like access control and monitoring, organizations build layered, adaptive protections. These methods represent both opportunity and responsibility, the chance to safeguard data more effectively, balanced against the need for discipline in deployment. When integrated thoughtfully, advanced protections enhance resilience without undermining operational efficiency. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.